In today's lecture at Medical Sciences, we want to look at calculating pH of buffer solutions. We want to see how we can determine the pH of buffer solution using Hasselbalch-Henderson equation, or what we call Henderson-Hasselbalch equation. So in this video, we are going to derive Henderson-Hasselbalch equation. We are going to look at its application in medicine and also how examples of how we can calculate the pH of buffer solutions. If you haven't watched on the video about the mechanism of buffer systems, you can visit it so that you can be on the same page. And we say the buffer solution is a solution which resists change in pH. When a small amount of a strong acid or a base is added, and we said these buffer solutions contain either a weak acid and a conjugate base, which we said weak acid and salt of a weak acid, or they can contain a weak base and a salt of a weak base. And as we begin, we remind you to subscribe. If it is your first time, please go to the subscription button and make sure you subscribe so that we can continue to support our growth of the channel. So I want to begin by deriving Henderson-Hasselbalch equation, whereby this Henderson-Hasselbalch equation, suppose we have a weak acid. If we have a weak acid known as HA, this is our weak acid. We are going to use this weak acid to derive the equation, whereby this weak acid dissociates. We're going to see that this weak acid dissociates partially, since it is weak, to liberate hydrogen ions plus a conjugate base. So this one becomes a conjugate base, whereas this one is a weak acid. So after having our conjugate base and a weak acid, we can look for the dissociation constant of this acid, whereby dissociation constant, that is Ka, the Ka of this acid is going to be, you get product, you multiply the products, that is concentration of hydrogen ions, multiplied by concentration of the conjugate base, then you divide by the reactant, which is the weak acid, concentration of the weak acid. This is how we calculate the dissociation constant, that is Ka. Ka, we are calling it dissociation constant. This is a dissociation constant. So after getting Ka, remember we are interested in calculating the pH. So I have here to go ahead and make concentration of hydrogen ion subject of the formula. Make it subject of the formula. And how do we get? We are going to first, if we have this, we are going to first bring the weak acid this side, and we shall get Ka concentration of the weak acid equaling to the concentration of the hydrogen ions multiplied by concentration of the conjugate base. Remember, we want to make hydrogen ions the subject of the formula, so we are going to divide conjugate acid, conjugate base, both sides. So we are going to get Ka concentration of the weak acid equaling to the concentration of the hydrogen ion and the concentration of the conjugate base, and we divide both sides by the conjugate base, and also this side by the conjugate base. This conjugate base goes with this, and we are going to remain with concentration of hydrogen ion being the same as, just I'm rearranging, being the concentration of Ka divided by, in brackets, concentration of the weak acid. Then we divide by the concentration of the conjugate base. So after getting this, here I'm going to introduce rules of logarithms. But before that, I'm going to introduce log. Here what you are going to do is to introduce negative log base 10 both sides, and I'm going to get negative log base 10 concentration of hydrogen ion equaling to negative log base 10 Ka concentration of weak acid divided by concentration of the conjugate base. Then here we bring rules of logarithms. If we are multiplying, both are the same, we add. The base is the same. Here we have the same base, and we are multiplying, so we shall add. So we are going to get negative log base 10 concentration of hydrogen ion equaling to negative log base 10 Ka, and because we are multiplying and the base is the same, we add, plus negative log base 10 concentration of the weak acid divided by the concentration of the conjugate base. After reaching at this point, we have to know, but negative log base 10 is the same as P. So we are going to introduce P in where there is negative log. So we are going to get, at the end we are going to get pH, because negative log concentration of hydrogen ion is pH, and also negative log Ka is pKa, is equal to pKa. Then this one is going to remain the same, whereby it is going to become negative log 10 concentration of the acid over concentration of the conjugate base. But we don't want minus in our equation, so we are going to change this side, this sign, and when we change to plus this sign, we are going to take the reciprocal of this. So whereby the conjugate base is going to come up and the acid comes down. This is the reciprocal when we change the sign. So we are going to change the sign here, and we end up getting our equation being pH equaling to pKa plus, when we change to plus, we take the reciprocal of this, which is going to be log concentration of the conjugate base of a concentration of the weak acid. And this one becomes our Henderson Hasselbalch equation. This is the Henderson Hasselbalch equation, whereby we have seen how we derive it. After getting a weak acid, you have to know which is the weak acid and which one is the conjugate based on a dissociation. Then we look for the dissociation constant Ka. Then we make hydrogen ion the subject of the formula, because we are interested in calculating the pH. After making it the subject of the formula, we introduce negative log both sides. And here we apply the rule of logarithm, because when we are multiplying, we add. Then we know that negative log concentration of hydrogen ion is pH. And then negative log base 10 or base 10 of Ka is pKa. So therefore, where there is this one, we put pH. Where there is this, we put pKa. Then we remain with negative log concentration of the weak acid and the conjugate base. But remember, we don't want a negative in our equation, so we change the sign from negative. And if we change it from negative to plus, we take the reciprocal, whereby here the denominator becomes the numerator and the numerator becomes the denominator, hence getting our equation like this. So this is the Henderson Hasselbalch equation, which I can write here in red, that the Henderson Hasselbalch equation, we have said that pH is equal to pKa plus log concentration of the conjugate base over concentration of the weak acid. This is what we call Henderson Hasselbalch equation, whereby this one is denominating for the weak acid, and this is for the conjugate base. So this is the weak acid, this is the conjugate base. And you can ask yourself, what is the application of this? A Henderson Hasselbalch equation. This Henderson Hasselbalch equation is the one that is applied in determining, he used it to determine pH of buffer solutions. It is used to calculate the pKa of buffer solutions, whereby this pKa can help us to determine the strength of the buffer. And the buffer is stronger when the pKa is equal to pH. Or we can also use it to calculate the concentration of the weak acid, or we can determine the concentration of the conjugate base. Because we have said we have pH, so we can calculate pH. We have pKa, so we can also determine, if we have pH, we have these concentrations, we can also determine the pKa. And if we have pH, we have pKa, we can easily determine even the ratio of the conjugate base and the weak acid. And also, if we have one of these, we can determine the conjugate base, and if we have this, we can determine the weak acid. So this is the application of the Henderson Hasselbalch equation in medicine. So after deriving the formula, we are going to see how can we apply in calculating pH of buffer solutions. And here we are given an example to calculate the pH of a buffer solution which contains 0.2 molar acetic acid and 0.1 molar acetate, which is, so this one is going to be the weak acid, this is the conjugate. So the first thing to determine in the question is to know which one is the weak acid and which one is the conjugate base. After seeing that one, we shall also need pKa, but we thank God they have given us association constant or dissociation constant, so we can use it to calculate pKa. So here the first thing is to calculate pKa, whereby pKa is equal to negative log base 10 Ka. Therefore, pKa is going to be negative log base 10. Then we are given 6.3 times 10 to power negative 4. And according to rules of logarithms, here you can put it on the calculator directly, or according to rules, when you're multiplying and base is the same, you add. So we're going to get negative log base 10, 6.3 plus negative log base 10 of negative of, here it becomes 10, then 10 over negative 4. And this one is going to be negative log base 10, 6.3. Then this negative 4 counts at this point, and you want to find there another negative, it becomes a positive. So it becomes plus log 10, 10. But here before plus, we have there the 4. Here we have 4, negative 4, negative 4, it becomes plus 4, log of 10, 10. But log of 10, 10 is 1, but log of 10, 10 is equal to 1, so we're going to get negative log 6.3 plus 4. 4 times 1 is 4. So the end result here, we are going to get pKa of 3.2. How? Get your calculator and you put negative log 6.3, then you add 4, you are able to get pKa of 3.2. After getting the pKa value, so we can now bring the Henderson Hasselbalch equation, which says that the pH of the solution is equal to the pKa, which we have got, plus log concentration of the conjugate base, which is ethanoate, acetate, then over concentration of the weak acid, acetic acid. And then we substitute pKa is 3.2 plus log base 10. Concentration of the conjugate base is 0.1. 0.1 molar. Then the concentration of the weak acid is 0.2 molar. And we are going to end up getting, when you put this on a calculator, get log of 0.1 molar divided by 0.2, we are able to then plus 3.2, we are able to get the pH of 2.9. So the pH will be 2.9. So the pH of this buffer solution is 2.9, whereby here you get a calculator, 0.1 divided by log of 0.1 divided by 0.2, then you add 3.2, you're able to get 2.9. So that is the pH of this buffer solution, whereby we have used Henderson Hasselbalch equation. Then we have another example here. We are required to calculate the pH of the solution when provided with this one is 0.2, which is the weak acid, and 0.4 molar of the conjugate base. So from Henderson Hasselbalch equation, whereby we say pH is equal to pKa plus log base 10, concentration of the conjugate base, and in this step, the conjugate base is the carbonate. We divide by the concentration of the weak acid, which is carbonic acid. Then the pKa is given 4.7. In this question, in this one they had given us Ka, but here we have been given pKa directly. So we don't need to calculate the pKa value like the way we did here. Plus log base 10, the concentration of the weak base of the conjugate base is 0.4 molar divided by 0.2 molar of the weak acid. And this one is going to give us 4.7 plus log base 10 of base 10, this one becomes 2. And the final answer is going to be 5. If we put it on a calculator, the pH value is going to be 5. So the pH of this buffer solution of the bicarbonate buffer is 5 after applying Henderson Hasselbalch equation. So this is what we can discuss in this session on the deriving of the Henderson Hasselbalch equation and some examples on how we can use it in calculating pH of solutions. And also we have seen that we can also use it in calculating the pKa of the solutions and the concentration of the weak acid and the conjugate base. Thank you so much. Continue to learn with us and share to many so that they can continue learning. Thank you so much.